Prove that if f of x is an increasing function, and if the curves y equal f of x and y equal to f inverse of x intersect, then they must intersect on the line y equals x. Now this is a question that I always do with my class when introducing the inverse functions topic, which is usually in early year 11. And even though the method used to complete this proof is something that you encounter in extension 2, it dispels a common misconception that all the students have about inverse functions, which is that a function and its inverse will always intersect on the line y equals x. Now that statement in itself, that a function and its inverse will always intersect on the line y equals x, is obviously not true because the function and its inverse may not even intersect at all. But even if we were to say that when the function and the inverse intersect, that they are always going to intersect on y equals x, that's also not true. And we can see that with a couple of counterexamples. And the first one is quite a trivial counterexample, which is where we have a function and its inverse being exactly the same function. So 1 on x is its own inverse. And you can see that the graphs here lie on top of each other. So yes, at these 2 points, when x is equal to 1 and negative 1, they intersect on the line y equals x. But on every other point on the curve, every other point, they intersect off the line y equals x. So clearly that's a counterexample to the claim. But this is quite a trivial counterexample. We even have some non-trivial counterexamples, such as the function, let's call it g of x equal to negative x cubed, and g inverse being negative the cube root of x. And you can see that yes, there is a point where they intersect on the line y equals x, but then there are also points where they don't, which you can see there again occurring at x equal to 1 and negative 1. So it's not necessarily true that our function and our inverse have to intersect on the line y equals x. But what we're trying to prove is that if our function is an increasing function, and we know that they intersect, but if it's an increasing function, then that's enough to guarantee that they will intersect on the line y equals x. So that's what we're going to try to prove now. Now, to prove this, we do want to make a couple of very obvious observations, but it's good to have them written down so that when we use them, we know what we're talking about. So the first one is going to be that a function, f of x, and its inverse, f inverse of x, they will intersect when y is equal to f of x, which is equal to f inverse of x. And this is obvious. This is just saying that the y values need to be the same. That's all this statement is saying. At the point of intersection, the y values of the two functions are the same. They're producing the same function value, you could say. And the second one is going to be that if f of x is an increasing function, which is what we're going to be concerned with in our proof, if f of x is increasing, then having an inequality and applying the function to both sides of that inequality preserves the direction of the inequality. And you can see this quite clearly through a graph. If you have a look over here, we have any random increasing function, and you can see that when a is less than b, then our function value a is going to be smaller than our function value at a, f of a, is going to be smaller than the function value at b, f of b. And that's a very obvious thing that we can see from a graph, but maybe you've never thought about it when you're doing increasing functions or decreasing functions, okay? Just by the way, if it was decreasing, you would swap the direction of the inequality. So now that we have these two important points set out, we're able to go ahead and start the proof. So the way we're going to do this is we're going to show that it's not possible for a function to intersect its inverse when it's above the line y equals x and when it's below the line y equals x, which leaves only one possibility, which is on the line y equals x. Okay? So basically we have two cases. So we have case 1, which is when y is going to be greater than x. Okay, so we're checking, is it possible for an increasing function to intersect its inverse with y being greater than x, above the line y equals x. So what do we know? Well, if y is greater than x, well, we know that y is equal to the inverse function. So I'll say, well then, therefore, f inverse of x is greater than x. okay? But now I'm going to apply f to both sides of this inequality. And because f is increasing, we have this property here. We are allowed to preserve the direction of the inequality. So if I apply f, I get f of f inverse is greater than f of x. And here I'm going to say, since f is increasing, just because I want to give some sort of reasoning, since f is increasing. But now, I use the fact that f composed with f inverse returns the identity function, returns x. So this is x, and this is staying as f of x. And I could say, by definition of inverse function. And now, I just recognize, well, hold on, f of x is the same as y, again for this reason that we had up here. So see how it's such an obvious fact, but having it written out in front of us allows us to do this proof basically instantly. So this then, I can say, means that x is greater than y. But this is not possible because I started with y being greater than x, and I ended up with x being greater than y. And that's what we call a contradiction. So this is a contradiction, which means that this case is not possible. So it's not possible for them to intersect where y is greater than x, where the y value of the point of intersection is less than the is greater than the x value of the point of intersection. And so now we go to case 2, which is almost identical in its proof. This is when y is less than x. We're checking what happens if our point of intersection has a y value less than its x value. Well, it's basically exactly the same thing, so let's write it out. Y is the same as f inverse. Then I apply f to both sides of the inequality. And I'll say since f is increasing. And again, I use the definition of an inverse function to get, sorry, I should have put an f of x on this side here. Where are we? Let's just do f of x like that. So we have x less than f of x by definition of the inverse. And then x is going to be less than y. Again, because f of x is equal to y. And again, I get a contradiction. So both of these cases are not possible. It's not possible for me to have a point of intersection where the y value is greater than the x value or where the y value is less than the x value. So both of these cases are eliminated. Now I can't actually prove that they're going to intersect because they may intersect and they may not intersect. And that's totally fine. I'm not trying to prove that they're going to intersect on y equals x. I'm trying to prove that if they intersect on if they intersect at all, then it's going to be on y equals x, okay? If the curves intersect, then it's going to occur on y equals x. And that's basically what we have here. So I'll just put in here, I'll say to conclude, therefore, if the lines intersect, not the lines, the curves, I should say curves. If the curves intersect, they do so on y equals x. And that completes the proof.